Every culture that lifted its gaze to the night sky has felt awe at the unknown, a sense that somewhere in the vastness there are places where nature hides its most dangerous secrets. Black holes are the ultimate of those secrets. Regions where gravity rules so completely that nothing, not even light, escapes. For a long time, they were dismissed as abstractions, curiosities of mathematics rather than real features of the universe. But the truth is unavoidable now. They exist, they dominate, and they break the boundaries of our understanding. A black hole is not a material object in the ordinary sense. It is a region of space-time where escape becomes impossible. The event horizon marks its invisible boundary, the point where the pull of gravity outruns every possibility of return. Outside that horizon, survival may still be possible with enough speed, but once inside, every path curves inward, every fate is sealed. At the center of this structure sits the singularity, a place where density rises to infinity and the smooth fabric of physics collapses. Stars create such monsters when their nuclear lives end, when pressure can no longer fight back against gravity. The stellar core burns for millions or billions of years, but eventually its fuel is exhausted and balance is lost. For a massive star, collapse may stop at the neutron stage, an object already so dense that a teaspoon would weigh billions of tons. But for the greatest stars, even neutrons are crushed beyond endurance, and gravity continues inward until a horizon forms. Picture this collapse: the nuclear fire gone, the weight unstoppable, the star folding in on itself. Gravity tightens without limit, matter forced into smaller volumes, light bent into spirals that never return. The horizon emerges quietly, not with an explosion, but with a silence, a line across which escape is forever denied. And what remains is not a star at all, but an absence, a region defined only by what it refuses to release. Einstein's equations describe this perfectly: space-time curving inward, paths of light bending until they circle the horizon. The surface is not matter, but destiny, the mathematical point where geometry decides there is no exit. Crossing that line is like walking through a one-way door. No signal, no cry, no photon can return. And the singularity deep inside pushes equations to infinity, exposing the place where our physics fails. Early scientists doubted nature would permit such absurdities. They assumed collapse would halt before the unimaginable. The cosmos has shown otherwise. Black holes are not only possible, they are common. Now we know that galaxies are anchored by supermassive holes, millions to billions of suns collapsed into single horizons. And their existence so early in cosmic history is a direct challenge to every timeline of growth we thought secure. Quasars prove this challenge with their blinding light, distant beacons powered by black holes devouring matter. The disks of gas that whirl near horizons glow with intensity greater than whole galaxies. Jets of plasma erupt outward for millions of light years, guided by magnetic fields twisted by rotation. And the impact of this fury shapes galaxies themselves, regulating star formation, blowing winds into intergalactic space. Yet the mystery persists. How did they grow so massive so quickly? The James Webb Space Telescope has revealed black holes billions of solar masses strong, existing when the universe was only a fraction of its age. Standard models of accretion and mergers cannot account for this growth. Not enough time, not enough efficiency, not enough material. So the reality is uncomfortable. Black holes grow faster than our physics says they should. Nothing illustrates paradox better than their invisibility, unseen objects that control the fate of galaxies. The Event Horizon Telescope gave us the first direct image, a glowing ring of bent light surrounding darkness. It confirmed Einstein's geometry at the horizon, but left the singularity itself hidden in eternal shadow. And the question of what lies within remains unanswered, perhaps unanswerable by observation. Still, black holes offer themselves as laboratories. They reveal the cracks in our deepest theories. Stephen Hawking showed they are not entirely black. Radiation seeps outward in a quantum whisper. This faint radiation means horizons shrink, holes evaporate over eons, slowly fading away into nothingness. But the price of this insight is paradox. Information seems lost forever in violation of quantum law. Here, the contradiction is direct. Relativity predicts destruction of information. Quantum mechanics demands its preservation. Neither side can simply be abandoned. Each has been tested. Each is fundamental. The conflict at the heart of physics grows sharper. Two truths that cannot both stand as written. And the search for resolution has reshaped cosmology, forcing radical ideas into the center of science. Perhaps the strangest idea is holography, the suggestion that our universe is a projection from lower dimensions. The black hole horizon would act as a screen, encoding every particle that crosses, preserving it in subtle form. So, in this view, nothing is ever truly lost, only scrambled, stored, written on the boundary. And the implication is staggering. Space itself may be an emergent illusion, born of information. Even their collisions expand our knowledge. Gravitational waves ripple outward, carrying the signature of masses and spins. Detectors on Earth now feel these ripples, faint stretching and squeezing of space as waves pass through us. Each new signal confirms black holes in abundance, not rare accidents but frequent realities of the universe, and their patterns often surprise us, some too massive, some strangely aligned, some beyond prior prediction. Every discovery forces revision. Stellar deaths must produce stranger remnants than we imagined. The population is more diverse than expected. Heavy holes, light holes, spinning holes, quiet holes. They exist in places that rewrite our models of galaxies and stars, demanding new stories of formation, and their connection may reach all the way back to the beginning of time. Primordial black holes born in the first seconds. If such primordial holes exist, they could explain dark matter, the missing mass that shapes galaxies without shining light. Searchers look for them in gravitational lensing, in background radiation, in cosmic structure. So far, no proof is final, but the possibility keeps them at the center of cosmology. And the vision is profound. Black holes may not only be ends, but beginnings. When the Event Horizon Telescope revealed that orange ring, the world paused. A theory had become an image. The sight of it confirmed Einstein's genius again. Light bent into a circle by space-time itself. It showed us that prediction could become picture, that monsters once thought imaginary truly exist. But the mystery at their core remained untouched, the singularity silent behind the horizon's veil. Even now, the deeper we look, the more they resist our control. They break models as quickly as we write them. They mock our timelines, they defy our growth charts, they expand faster than our math. Inside a black hole, our mathematics begins to fail. Predictions stretch toward infinities, and reality slips through our grip. The equations of Einstein tell us that space-time curves inward endlessly, yet quantum mechanics insists that infinities cannot describe nature. At the center lies the singularity, a place where density grows without bound, where the familiar distinction between past and future ceases to make sense, and the problem is clear. Black holes reveal the tension between our greatest theories. Einstein's relativity describes the cosmic stage with elegance, the geometry of space-time bending smoothly under the weight of matter. Quantum mechanics governs the microscopic world. Particles in superposition, probabilities unfolding in constant motion. When the two domains overlap, as they do inside horizons, contradictions emerge. Laws that never conflict elsewhere collide violently. And the singularity is where those contradictions sharpen most, a cliff where mathematics no longer offers a foothold. Every singularity is hidden behind a horizon, a mercy that preserves predictability for the universe outside. This cosmic censorship ensures the breakdown of physics stays sealed away from external view. But inside, the rules of determinism collapse. No prediction can follow paths into the singularity. And the question rises: what does it mean for a universe when its laws collapse at hidden points? Stephen Hawking transformed this question in the 1970s when he applied quantum physics to black holes. He showed that black holes are not entirely black. Instead, they radiate faint particles from the horizon itself. This radiation, now called Hawking radiation, means black holes evaporate, shrinking slowly until they vanish. But the cost of this discovery was enormous, for it introduced the information paradox. Information describes the state of matter and energy, the arrangement of particles, the details of every event. Quantum laws say information can never be destroyed. No matter how scrambled, it must always be preserved. But when matter falls into a black hole, its information seems lost, hidden beyond the horizon, erased at the singularity. And Hawking's radiation carries no memory of what fell in. It is featureless, revealing nothing about the past. So the paradox sharpened. Relativity allowed destruction. Quantum mechanics forbade it. Neither side could yield without overturning a pillar of physics, and the clash remains unresolved even today. Physicists offered bold ideas to escape the deadlock: holographic universes, firewalls of energy, emergent space-time. But the truth is uncertain. Black holes force us to rethink reality itself. Holography may be the most radical answer. The idea that all the information of a volume can be stored on its surface. In this view, a black hole does not erase information. It encodes it at the horizon, like data etched on a cosmic screen. So the three dimensions we see might be emergent, an illusion rising from two-dimensional information at the boundary. And the universe itself may follow this rule, a grand hologram projected from surfaces beyond our sight. This vision reshapes philosophy as well as science, reality not as substance, but as information woven into space-time. Black holes become laboratories of this idea, where paradox reveals the hidden architecture of the cosmos. Perhaps space and time are not fundamental at all, but byproducts of deeper patterns of quantum information. And the singularity is only a signpost, pointing toward physics still undiscovered. Even without resolving the paradox, black holes test physics at its extremes, merging relativity and quantum mechanics in a single stage. The mergers of black holes send ripples of gravitational waves outward, carrying subtle details of their hidden interiors. Detectors like LIGO and Virgo measure these distortions, confirming masses, spins, and distances of colliding horizons. and the patterns in those waves may one day reveal hints of quantum effects, signs of a theory beyond relativity. Some proposals suggest firewalls at horizons, walls of violent energy where none should exist. If true, the horizon would not be smooth, but a barrier, incinerating anything that tries to cross. Others argue horizons are gentle, storing information quietly. No drama, no fire, only subtle encoding. And the debate continues, unresolved, because no experiment yet can see what truly happens at the edge. Inside, imagination must fill what observation cannot. Artists of theory sketch possibilities where data runs dry. One picture shows singularities as crushing points of infinite density, matter compressed beyond description. Another view sees them as bounces into new regions, perhaps wormholes to other universes hidden behind horizons. And the speculation stretches towards science fiction, yet remains grounded in the stubborn equations that predict their existence. When matter spirals into a black hole, it does not vanish instantly. It lingers in disks of plasma heated to blazing temperatures. The disk radiates intensely, releasing energy as matter falls closer to the horizon. Jets erupt from the poles, guided by magnetic fields, beams of particles stretching across intergalactic space. And the black hole feeds slowly, like a furnace consuming its fuel while cloaking its interior in mystery. Even time itself is distorted near the horizon, slowed by gravity until it nearly freezes from the outside view. The closer you are to the edge, the slower your clock ticks compared to distant observers. To an astronaut falling in, time feels normal. But from outside they appear to slow, to freeze, to fade. And the illusion is striking. Black holes rewrite not only space, but the passage of time. This effect links black holes to cosmology itself, for the early universe also bent time and space to extremes. The physics of horizons may illuminate the physics of the Big Bang. Both are singularities where known laws fail. So by studying these monsters, we may glimpse the first instant of creation, the moment before time stretched into expansion. And the hope is that black holes are windows to the origins of the universe. Every discovery so far deepens the riddle, confirming Einstein yet refusing to yield the deeper truth. The radiation, the paradox, the holographic hints, each pulls theory in new directions. Physicists stand at the edge of knowledge, staring into shadows that both confirm and destroy their equations. And the reality is humbling. Black holes are not only objects, they are teachers, exposing the fragility of our science. Some black holes are monsters of ordinary size, a few times the mass of our sun, born from collapsing stars. Others grow into supermassive scales, millions or billions of suns crushed inside horizons at galactic cores. But there are giants beyond even that, black holes so huge they should not exist at all, and yet they do. These ultramassive black holes are nature's most unsettling creations, structures that strain the limits of growth, time, and physics. The largest known examples weigh tens of billions of solar masses. Horizons larger than our solar system, wider than orbits of planets. Their centers sit inside galaxies so vast, yet even there they dominate. Their gravity shaping stars, gas, and motion on scales of hundreds of thousands of light years. Astronomers call them ultramassive because words fail. Supermassive is not enough when describing horizons of such scale. And their existence is deeply troubling because the universe is not old enough to explain how they formed. How do black holes grow so immense? They feed on gas and dust spiraling inward, disks that glow brighter than all starlight combined. Accretion should build them slowly, one star, one cloud at a time, yet physics sets a limit on how fast feeding can proceed. That limit is called the Eddington rate, the point where radiation pressure from falling matter balances gravity's pull. Push harder than that, and infall slows. Light itself pushes material away from the horizon. So by calculation, black holes should take billions of years to reach billions of solar masses. But quasars show us holes of such size less than 1 billion years after the Big Bang, far too soon for slow feeding to explain. And the paradox grows sharper. The cosmos presents giants that outpace its own clock. Perhaps they began large, skipping smaller stages altogether, collapsing directly from vast clouds of primordial gas. In this picture, early dark matter halos and pristine hydrogen streams could collapse into holes of 100,000 suns or more. Those seeds would then grow faster, leaping ahead of ordinary stellar remnants. And the theory of direct collapse black holes is now one of the strongest contenders for their origins. Other ideas propose primordial black holes, formed in the violent first second of the universe. Quantum fluctuations stretched by inflation could have produced dense knots, regions collapsing into holes before stars even existed. Such primordial seeds might still lurk today, invisible yet massive, anchoring galaxies from the beginning. And the possibility links black holes not only to galactic evolution, but to dark matter itself. Observations press these theories harder each year. New quasars revealed by Webb telescope light up the early cosmos. The records fall regularly. Black holes of 1 billion masses seen when the universe was less than 1 billion years old. Each new finding tightens the puzzle, forcing theorists to refine how quickly accretion or mergers can occur. And the gap between what we see and what we can explain only widens. These ultramassive holes also challenge galactic balance, for their feedback reshapes the very galaxies that host them. Jets fire outward, heating and stirring intergalactic gas, preventing new stars from forming in central regions. Entire clusters of galaxies feel the influence of these central giants, their temperatures, motions, and structures shaped by invisible horizons. And the relationship between galaxy size and black hole mass suggests co-evolution, as if galaxies and holes grow hand in hand. Yet, some ultramassive black holes appear too large even for their galaxies, breaking the scaling relations astronomers expect. The holes seem oversized, as if they grew independently, unconstrained by their host systems. Such outliers raise unsettling questions. Are we missing physics of feedback, or are some holes truly unbound from galactic rules? And the mystery deepens when we consider that some galaxies show almost no central black holes at all. Even, stranger, ultramassive black holes may grow through collisions, galaxies merging, horizons swallowing one another. These mergers would send colossal gravitational waves rippling across the cosmos, waves so vast they dwarf anything detected so far. Pulsar timing arrays now hunt for this background hum. Subtle distortions in the timing of cosmic clocks spread across the sky. And the hint of such signals may already be appearing, evidence of giants colliding in distant darkness. Imagine 2 ultramassive black holes spiraling together, horizons billions of miles wide locked in a dance of gravity. The energy released in their final collision would exceed all the stars of the observable universe combined. Space itself would ring like a drum, sending ripples through billions of light years. And the echo of that collision might still be detectable today, whispering through pulsar timing networks. But ultra-massive black holes are rare. Perhaps only a handful exist in the observable universe. The rarity makes each discovery precious, each measurement a clue. Still, even a few examples strain physics to the breaking point, demanding explanations that stretch beyond conventional models. And the fact that they exist at all tells us we are missing something fundamental about growth in the cosmos. When astronomers measure the motions of stars near these giants, they see orbits faster than bullets, whirling at thousands of kilometers per second. Those motions reveal the invisible weight at the core, proof that gravity holds more mass than all visible matter combined. Spectra show glowing gas spiraling toward the horizon, heating to millions of degrees before vanishing. And the numbers confirm the shocking truth. The mass of tens of billions of suns collapsed into a single region. Perhaps these giants are more than anomalies. Perhaps they are keys to cosmic evolution. The fact that nearly every large galaxy hosts a supermassive hole hints at necessity, not accident. If black holes seeded galaxies rather than the other way around, they would be architects of cosmic structure itself. And the idea that the largest holes shaped the universe as we know it is now taken seriously. The largest ever proposed lies in galaxy cluster TON 618, an estimated 66 billion solar masses. Its horizon could engulf our solar system many times over, swallowing orbits out to Pluto. Though distant, its quasar shines with almost unimaginable brilliance, a furnace powered by a hole beyond comprehension. And the existence of TON 618 stands as a monument to paradox, proof that the universe builds faster and larger than models allow. Every new ultra-massive discovery sharpens the tension between theory and observation, between what we predict and what we find. The patterns of scaling relations, accretion models, and galaxy evolution are bent out of shape by these extremes. We know our understanding is incomplete, that something deeper is missing in our equations, and the giants sit quietly at galactic hearts, reminders that the cosmos still outpaces human reason. Still, progress may come from gravitational waves, whispers of ultramassive collisions traveling through space-time. Pulsar clocks across the galaxy are now the detectors, their ticking altered by ripples of distant mergers. These measurements may soon confirm the slow dance of giants, horizons spiraling toward collision over cosmic timescales. And the evidence of their hum may finally bridge theory and reality. Every galaxy carries a secret at its core, a black hole not only consuming but creating, not only destroying but shaping. For decades, astronomers thought of black holes as silent tombs, final resting places for collapsing stars. But in truth, they are engines, machines of gravity and motion that regulate the life of galaxies. And their power comes not from what falls in, but from what almost falls in and escapes. As gas spirals inward toward the horizon, it does not vanish immediately. Friction and compression heat it to astonishing temperatures. The disk of matter glows across the spectrum, from radio to X-ray, brighter than billions of stars combined. Jets emerge from the poles, launched by magnetic fields twisted by rotation, beams of plasma shooting into intergalactic space. And the energy in those jets is enough to shape the future of galaxies millions of light years away. Quasars are the most extreme of these engines, cosmic lighthouses blazing in the darkness of the early universe. Each quasar is powered by a supermassive black hole consuming matter at near the maximum allowed rate. Their light outshines entire galaxies, visible across billions of years, carrying the signature of the first structures. And the existence of quasars tells us that black holes were active architects, not passive prisoners in cosmic history. When a black hole feeds, its influence extends far beyond the horizon, heating, stirring, and reshaping the galaxy around it. The winds from quasars push gas outward, slowing or stopping star formation. Clusters of galaxies are affected as well, central black holes regulating the temperature of intergalactic gas. And the feedback from these engines explains why galaxies stop forming stars when they reach a certain size. Even galaxies with quiet cores carry the signature of black hole feedback, the balance of star birth and star death linked to activity at the center. The relationship between black hole mass and galactic bulge mass confirms this, a scaling law that ties stars to horizons. So black holes cannot be thought of as separate from their galaxies. They are partners, co-evolving across billions of years, and their influence stretches across scales so large it challenges our imagination. Jets carry matter across millions of light years, carving cavities in clusters, inflating bubbles of radio emission. The plasma in those jets moves near light speed, guided by invisible magnetic fields. Such jets pump energy into surrounding gas, keeping it hot, preventing collapse, halting new stars from forming. And this regulation may be the most important role black holes play. Cosmic thermostats controlling galaxy evolution. Imagine a galaxy cluster, hundreds of galaxies bound by gravity, clouds of hot gas filling the space between them. At the center sits a giant black hole, its jets inflating bubbles larger than whole galaxies. Those bubbles push aside gas, stir turbulence, heat the medium so that collapse slows. And the cluster evolves differently because of one engine at its heart. This feedback explains mysteries of cosmic structure, why galaxies grow to certain sizes and then stall. Without black holes, galaxies would keep forming stars endlessly, becoming too large, too bright, too unstable. But jets and winds cut off the supply of cold gas, enforcing balance, shaping the population of galaxies we see today. And the fact that this process works across billions of light years is staggering. Even at smaller scales, black holes reshape their surroundings, triggering as well as quenching star formation. Gas compressed by outflows may collapse into new stars in some regions, so the engines can both destroy and create, depending on conditions. They sculpt galaxies in complex ways. And the outcome is not chaos, but a cosmic equilibrium reached through violence. Radio galaxies reveal this process most clearly, their lobes of emission stretching vast distances. The jets powering them persist for millions of years, carving cavities into intergalactic gas. Such structures are ghostly reminders of ancient feeding events, evidence of black holes long after they quiet. And the imprint of those engines remains visible across cosmic time. When astronomers map X-rays from clusters, they see cavities where jets cleared hot gas, holes in the background glow of plasma. The shapes of these cavities match simulations of black hole feedback. Such images prove the engine's role in heating and stirring cluster gas, and the energy required is beyond comprehension, equal to trillions of supernovae released from a single horizon. Every feeding episode is a balance of supply and resistance, accretion pulling gas inward, radiation pushing it back. The Eddington limit defines this struggle, a ceiling on how fast matter can fall in. But some black holes exceed it briefly in episodes of furious accretion called super Eddington phases, and these bursts may explain the rapid growth of giants in the early universe. Perhaps ultramassive black holes owe their size to such bursts, short but furious episodes of runaway feeding. Gas funnels into the core, collapsing into the hole faster than radiation can push it back. Such events would light the sky with quasar brilliance, jets piercing the cosmos, and the evidence for them is found in distant quasars glowing with near impossible intensity. Still, the engines are not constant. They flare, they sleep, they awaken again. Astronomers see galaxies where central activity has shut down, leaving only ghostly radio lobes. In time, those lobes fade, only to be reignited when feeding resumes, and the cycle of activity repeats. Galaxies living through phases of silence and fury. So, black holes shape not only space, but time in galaxies, their rhythms set by feeding and feedback. The cosmic history of star formation shows peaks and valleys tied to black hole activity. Galaxies live longer, quieter lives because their central monsters enforce balance. And the truth is that the engines of galaxies are not optional, they are essential. Even our own Milky Way carries such an engine, a supermassive black hole called Sagittarius A. Though quiet now, it shows signs of past outbursts, bubbles of gamma rays ballooning above and below the galaxy. Those Fermi bubbles are relics of jets and winds that once erupted from the core. And the evidence reminds us that even silent engines can awaken without warning. Every time we study these engines, we discover new layers of complexity, feedback loops we had not considered. The links between accretion, jets, winds, and star formation continue to surprise. Models struggle to capture the full interplay. Galaxies are not passive hosts, but dynamic partners in this process. And the engines at their cores remain the key to balance across the universe. Still, many questions linger. How exactly are jets launched? Why are some holes radio loud and others silent? The mechanism of magnetic fields extracting rotational energy remains debated. Some ideas invoke the Blandford-Znajek process, spinning holes powering jets through magnetic tension, and the mystery of why only some holes ignite remains unsolved. When we observe quasars in detail, we see structures both ordered and chaotic, disks, winds, jets all interwoven. The interplay of forces pushes our simulations to their limits. Each new observation tests our theories, often forcing revision. And the lesson is humility. Black holes remain steps ahead of our models. Every time physicists believe they have understood black holes, a paradox rises, a contradiction that tears confidence apart. The most famous of these is the information paradox, a battle between relativity and quantum mechanics that remains unresolved. Stephen Hawking first revealed it in the 1970s, when he applied quantum principles to the event horizon. He showed that black holes are not perfectly black. Instead, they radiate faint energy that causes them to shrink. This radiation, now called Hawking radiation, emerges from quantum fluctuations near the horizon, particles paired at the edge of escape. One particle falls inward, the other escapes outward, leaving the black hole slightly lighter. Over time, this slow process evaporates the whole completely, turning horizons into whispers and then nothing. And the problem arises because the radiation is featureless. It carries no imprint of what fell inside. Information is the key here, not matter itself, but the details of its arrangement. Quantum laws say information is sacred. No event, no particle, no quantum state can be truly erased. But when matter crosses a horizon, its information seems lost forever, hidden behind the singularity, unreachable to the outside. and Hawking's radiation does not restore it. It emerges empty of memory, indifferent to what was consumed. So, the paradox becomes a duel between physics itself, relativity accepting loss, quantum mechanics refusing it. Neither side can surrender, for both have been tested across countless experiments. Relativity describes planets, stars, galaxies with perfect accuracy, while quantum mechanics explains atoms and particles with unmatched precision. And the singularity inside the horizon forces them into confrontation, where their rules cannot both be true. Physicists responded with radical ideas, attempts to preserve information without breaking laws. The holographic principle became one of the boldest answers, suggesting that horizons encode every detail that falls in. In this view, a black hole is like a cosmic storage device, its surface carrying all the information of its contents. So the loss is not real. It only appears lost because it is scrambled at the boundary. Perhaps the universe itself is holographic, three-dimensional space emerging from two-dimensional information. The idea stretches beyond black holes to the cosmos as a whole, reality not as volume, but as encoded surface. In that case, black holes are not destroyers of information, but guardians, keeping everything inscribed on horizons. And the mystery shifts from loss to decoding, how the information might ever be read back. Even this elegant solution creates new puzzles, leading to the proposal of firewalls. A firewall is a wall of high-energy particles at the horizon, incinerating anything that falls inward. This proposal was meant to save information, to keep physics consistent, but it violated relativity's promise that horizons feel smooth, and the debate became fierce, some defending firewalls, others rejecting them as impossible. When we imagine falling into a black hole, relativity tells us the horizon is uneventful. You would pass it without noticing. But the firewall argument insists the horizon is violent, a blaze of quantum fury burning away anything that touches it. If this vision is true, relativity's calm surface is a lie. The edge of a black hole is the hottest place in the universe, and the consequence is devastating. It means one of our theories must yield completely. Some argue that firewalls are unavoidable, that the smooth horizon cannot preserve information without contradiction. Others hold that firewalls betray the elegance of relativity. They refuse to accept such violence at the edge. Still others propose alternatives, complementarity, fuzzballs, emergent spacetime, and the argument remains unresolved. Black holes force us into a battlefield of ideas. Fuzzballs come from string theory, where black holes are not singular points, but tangled webs of strings. In this picture, the horizon is not smooth, but a dense structure, preventing collapse into an infinite point. The information would then be preserved in the fuzz, spread across the tangled strings instead of lost at a singularity. And the idea dissolves the paradox by changing what a black hole is entirely. Still, no evidence confirms firewalls, holograms, or fuzzballs. All remain theories tested only on paper. The challenge is observation, for horizons hide their secrets behind perfect darkness. So progress must come indirectly through gravitational waves, X-rays, and cosmic echoes. And the hope is that one day subtle signals will reveal which theory is true. Consider the analogy of a book thrown into a fire, the pages burned, the story seemingly gone. Thermodynamic laws tell us that information is not destroyed. The smoke and ash still carry the details in principle, but in a black hole, the ash cannot be recovered. The smoke cannot escape the horizon. And the difference is that physics itself may break down if the story truly ends there. Every approach to the paradox changes our picture of the universe, sometimes subtly, sometimes radically. The holographic view suggests reality is information. Firewalls suggest relativity is incomplete. Fuzzballs suggest strings are the foundation. Each solution points in a different direction for physics, toward quantum gravity, toward string theory, toward emergent space-time. And the truth is that none are yet proven, leaving us with uncertainty. Still, black holes give us the sharpest questions, and questions drive science forward. They force us to face contradictions that cannot be ignored. Perhaps inside horizons lies the key to a theory of everything, uniting gravity with quantum mechanics at last. And the search for that theory is one of the greatest challenges in physics. When gravitational waves pass through us, they carry whispers of collisions, signatures of horizons merging, some hope that tiny deviations in those waves could reveal quantum fingerprints. Others look to X-ray echoes from disks, reflections near horizons that test relativity's precision. And the possibility remains that black holes themselves will give us the data we need. So, the paradox of information is not just a puzzle, it is a gateway to new physics. The battle between relativity and quantum mechanics sharpens in the darkness of horizons. Each idea to resolve it reshapes our vision of space, time, and matter. And the story continues unresolved as Part 5 leaves us standing at the brink of answers we do not yet have. Time is the most familiar and the most mysterious dimension, the flow that orders our lives, the rhythm against which all events unfold. Einstein showed us that time is not absolute. It bends with motion, it stretches with gravity, it is woven into space-time itself. Black holes take this bending to the extreme, slowing clocks, distorting rhythms, pushing causality toward breaking points, and the closer you approach a horizon, the stranger time becomes. From the outside, the story seems simple but unsettling. An astronaut falling toward a black hole never quite crosses the horizon. To a distant observer, the clock of the falling astronaut slows. Seconds stretch into minutes, minutes into eternity. The image of the astronaut freezes just above the horizon, fading, dimming, red-shifted until invisible. And the illusion is complete. From the outside, they never fall in at all. Yet to the astronaut, nothing strange happens at the horizon. Their own clock ticks smoothly, their heartbeat unchanged. They cross the horizon in finite time, unaware that the universe outside sees eternity. The discrepancy is not an error, but a feature of relativity. Time itself depends on perspective. And the truth is that both views are real, each valid for the observer who measures it. Even light is stretched near horizons, its wavelength pulled longer, its energy drained. This redshift explains why falling objects fade from view, their glow stretched beyond visible detection. The effect is profound. Horizons are not simply invisible because of escape velocity, but because time itself slows light to nothing. And the silence of horizons comes not from darkness alone, but from the freezing of time. Imagine a clock hovering near the edge of a black hole. Its ticks slower and slower compared to one far away. The difference grows enormous as it approaches the horizon. Seconds for the clock become centuries outside. This time dilation is not science fiction, but measurable physics, confirmed by experiments with satellites and atomic clocks on Earth. And the principle extends to cosmic extremes, where black holes slow time almost to a halt. When gravitational waves pass near black holes, they too carry the imprint of distorted time. Their oscillations stretch and compress, bending with the curvature of space-time. Such signals are like recordings from the edge of eternity, rhythms slowed, reshaped, warped, and the lessons they carry may reveal subtle quantum effects hidden in the stretching of clocks. Every story of time near black holes leads to paradoxes of causality, questions about what happens first, last, or forever. Inside a horizon, time and space exchange roles. Moving inward is as inevitable as moving forward in time. No choice remains once the horizon is crossed. The singularity lies in the future as surely as tomorrow lies ahead of today. And the future itself becomes death by geometry, not by decision. Perhaps the strangest feature is how black holes create two truths. One for the outside, one for the inside, never reconcilable. For the outside observer, matter never enters, it freezes just above the horizon. For the inside traveler, the horizon is crossed without hesitation, and the singularity awaits in finite moments. And the paradox is that both are correct, yet cannot be combined into one picture. So time becomes relative in the deepest sense, not only slower or faster, but fundamentally incompatible between perspectives. The implication is that reality itself depends on where you stand, on which clock you carry. This lesson unsettles us because we crave a single narrative, a universe where events happen in one order, one rhythm. But the universe we inhabit is richer, a place where clocks disagree, yet truth remains intact. Even Hawking radiation fits into this story, its particles born from time stretched and torn at the horizon. The longer an object hovers near the edge, the more its information seems spread, smeared across the horizon by distorted clocks. Some physicists believe this smearing encodes the missing data, time dilation itself writing memory onto the surface. And the horizon may be less a wall than a clock turned infinite, recording what enters as frozen silhouettes. When science fiction imagines time travel, it often leans on black holes, wormholes, shortcuts, loops. The theory of relativity permits closed time-like curves in some extreme solutions. In principle, spinning black holes may allow paths that circle back in time, but the practicality is doubtful. Such paths collapse into instability, and paradoxes multiply. Still, black holes stretch our thinking toward such possibilities. They show how fragile our sense of linear time truly is. They remind us that time is not a background stage, but an active player. If gravity bends light, it bends clocks just as surely, curving the measure of seconds themselves. And the fact that time nearly halts at horizons shows us its malleability. Every attempt to unify relativity and quantum mechanics must grapple with time, because both theories treat it differently. Relativity sees time as geometric, smooth, continuous. Quantum physics treats it as a parameter, ticking forward without resistance. And the collision of these pictures inside black holes shows that our grasp of time is incomplete. Perhaps time is emergent like temperature, not fundamental, but arising from deeper statistical laws. The holographic principle hints at this, suggesting time may come from correlations of quantum information. If true, then black holes are clocks of the universe, revealing how time itself is built from hidden rules. And the paradox of slowing and freezing may be the key to that construction. Imagine being suspended near a horizon, watching the universe above you accelerate, stars aging, galaxies evolving, billions of years passing. The closer you hover, The more exaggerated the effect, the faster the universe outside races ahead. In principle, a traveler could descend, pause, and return, discovering that cosmic epochs passed while only hours passed for them. And this time travel is not fantasy, but relativity made real in principle, if not in practice. Even our universe as a whole may mirror this behavior, the early Big Bang acting like a horizon. The cosmic microwave background is a snapshot of frozen time, photons stretched and slowed from the moment of release. In a sense, the Big Bang and a black hole are twins, singularities where time itself begins or ends, and the comparison suggests that black holes might hold echoes of our own origin. Every black hole is silent by itself, swallowing light, trapping signals, hiding within darkness. But when two of them orbit together, their silence becomes thunderous. Space itself begins to ring with their motion. This dance is invisible to our eyes, yet its rhythm spreads across the universe, waves of gravity stretching and squeezing space-time. And the moment they collide is one of the most violent events in all of nature. When two black holes spiral inward, they orbit one another for millions of years, locked in a slow, tightening embrace. The orbits decay as energy leaks away in gravitational waves. With time, they draw closer, circling faster and faster, each revolution shorter than the last. And at the end, in the final seconds, they whirl at near the speed of light before merging. The result is a single larger black hole, its horizon swollen by the mass of both. For a brief instant, space-time itself vibrates, releasing more energy than all the stars of the visible universe combined. This energy does not appear as light, but as gravitational waves rippling outward. And the echo of that merger can be heard across billions of light years. Gravitational waves were predicted by Einstein in 1916, tiny ripples in the geometry of space and time. For a century, they remained only on paper, too faint to detect with technology of the time. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first detection. Two black holes had collided 1.3 billion years ago, and their waves stretched Earth's space by less than a proton's width. That measurement was a triumph of science, proof that space-time itself can carry soundless music. The signal was faint yet unmistakable, a rising chirp, the death cry of two colliding horizons. For the first time, humanity had heard the universe speak in gravity rather than light, and the discovery opened a new era of astronomy, one where we no longer see alone, but listen. Every new detection since has expanded our view. Dozens of mergers recorded, each a story written in waves. The masses of the colliding black holes range from a few suns to nearly 100. Their spins twist the signals, their orbits imprint subtle patterns, and the details reveal a population of black holes stranger than we had expected. Some collisions involve unusually heavy black holes, too massive to be formed by ordinary stars. Others show unexpected spins, misaligned or tilted relative to their orbits. These anomalies suggest black holes may collide in chaotic environments, dense clusters, galactic centers, places where gravity is crowded. And the findings remind us that even destruction creates data, even silence tells a story. Imagine a dense star cluster, thousands of suns crammed into a single cubic light-year, black holes wandering like predators in a crowded jungle. In such a place, random encounters fling pairs together, binding them into orbits. Over millions of years, they spiral closer, feeding the background hum of gravitational waves. And the moment they collide, the universe gains a heavier black hole, and we gain another signal. When we listen to these signals, we are hearing pure gravity, space-time flexing as if it were a medium. No matter is needed, no light, no atoms, just geometry vibrating. This purity makes gravitational waves unique. They travel through everything, undisturbed by gas, dust, or distance. And the advantage is that they carry perfect records of their sources, untouched by intervening matter. Even the smallest wiggles in these waves carry meaning: the mass, the distance, the spin of the merging holes. Physicists decode the signals with models, matching chirps to equations of relativity. Each match is like solving a puzzle, reconstructing the hidden event that produced the waves. So far, every detection has confirmed relativity's predictions. Black holes merge exactly as Einstein described, but the opportunity lies in the small deviations, subtle differences that might reveal new physics. Perhaps quantum effects leave signatures in the late stages of merger, and the hope is that careful listening may expose cracks in relativity's smooth picture. Every merger also grows the population of heavy black holes, creating new horizons larger than before. The process of cosmic recycling builds monsters over time, step by step. Through repeated collisions, a hole may grow from stellar mass to intermediate and then to supermassive scales. And the possibility is that some of today's giants were built not only by feeding but by collision. Perhaps the largest black holes at galactic centers began as merger products, seeds born in violent unions. Galactic collisions then accelerated the process, dragging black holes to the middle, forcing them to merge. Over billions of years, these hierarchical mergers built engines of millions or billions of suns. And the giants we see today may carry in their horizons the history of countless collisions. When galaxies collide, their stars pass largely unharmed, but their central black holes cannot avoid each other. The holes spiral inward, trailing stars and gas, eventually binding into pairs. Over time, gravitational radiation shrinks their orbit until they merge into one. And the event is among the loudest in the universe, though loud in gravity, silent in sound. Already, pulsar timing arrays may be detecting the hum of these giant mergers, a background of gravitational noise. The timing of pulsars, cosmic clocks that flash with perfect precision, reveals faint distortions. This hum is the chorus of billions of supermassive black hole binaries merging across cosmic history, and the data hint that we are on the edge of confirming this background. Even our own galaxy will one day contribute to this song when the Milky Way merges with Andromeda. The collision will drag Sagittarius A and Andromeda's central hole together. After billions of years, they will spiral into one another, radiating waves across the cosmos, and the future universe will carry their echo long after our stars are gone. So, gravitational waves change the way we view black holes, no longer as silent absorbers, but as musicians of space-time. Each signal is a note, each merger a chord, building a symphony across billions of years. We listen to this music with detectors on Earth and in space, and the melody of these monsters carries not only destruction, but creation of new horizons. Every collision also reveals diversity, showing us that black holes are not uniform, but varied in mass, spin, and origin. The patterns of detections may eventually trace their formation histories. Some came from stellar collapse, others from dynamical encounters in dense clusters, and the population data are growing richer each year as detectors sharpen their sensitivity. Perhaps the next step will be space-based observatories, detectors like LISA orbiting the Sun. These instruments will feel lower frequency waves from supermassive binaries. Signals lasting for months or years will trace slow dances of giants before their mergers, and the detail in those waves will reveal the environments of galactic centers. When LISA flies, it will listen to the universe with unprecedented reach, catching signals Earth cannot hear. The background hum of merging galaxies may be mapped like never before. Such discoveries will tell us not only how black holes collide, but how galaxies assemble. And the dream is that one day we will play back the history of cosmic structure as a gravitational soundtrack. Every black hole is defined by its horizon, a surface that hides what lies inside, protecting the outside universe from its collapse. The horizon is not matter, not a shell, but a mathematical line, a boundary of fate more than substance. From the outside, it is the end of communication. Nothing that crosses can return, no light, no signal, no thought. And the mystery is whether this boundary exists to preserve not only physics, but reality itself. Roger Penrose proposed the idea of cosmic censorship, the principle that singularities are always hidden behind horizons. Without this veil, a naked singularity could be exposed, a place where equations break down visible to the whole universe. Such nakedness would destroy predictability. For outside observers, physics would lose its laws, cause and effect would fail. And the conjecture is that nature forbids this, hiding singularities in black holes. Yet, not all solutions to Einstein's equations obey this censorship. Some allow for horizons to vanish, exposing singularities. The Kerr solution for rotating black holes hints at loopholes. Extreme spins could strip away the boundary. If true, a naked singularity might stand bare in the cosmos. And the possibility unsettles physicists, for it would mean the universe allows its rules to be seen unraveling. When we model collapsing matter, horizons almost always form, shielding singularities from external view. The exceptions seem contrived, unstable, or artificial. Still, mathematics alone cannot prove censorship universal. And the debate continues, is the cosmos enforcing order? Or are we simply lucky to have not yet found a singularity in the open? Even, in theory, naked singularities present catastrophic challenges. Predictions become impossible, determinism dies. The loss of predictability means physics no longer provides answers. Initial conditions would not guarantee outcomes. Such a universe would be chaotic at the most fundamental level. And the fear is that without horizons, the cosmos would unravel into unpredictability. Perhaps horizons exist for this reason, not as accidents, but as safeguards. The universe might enforce them, keeping singularities hidden to preserve law. In this sense, black holes are not only destroyers but guardians of order, and the horizon becomes a cosmic firewall between chaos and structure. Still, extreme conditions test the rule. Mergers, spins, exotic matter could push holes to the edge of censorship. The spin limit is especially important. If a black hole rotates too fast, the horizon could dissolve. Astrophysicists watch carefully for signs of overspinning, of nature breaking its own censorship. But the data so far suggest that the cosmos resists such extremes. When gas accretes, it carries angular momentum, feeding spin to the central hole. The process could, in principle, overspin a black hole, removing its horizon. But magnetic fields, turbulence, and feedback appear to cap the spin just below the critical point. and the pattern holds across observations. Nature seems to balance itself at the edge of censorship, but never beyond. Every measurement of black hole spin confirms the same: fast but not infinite, rapid but still limited. The lesson is that horizons hold even when pushed to extremes. If censorship is a law, it may be enforced not by mathematics alone, but by the dynamics of real matter and energy. And the fact that horizons remain intact suggests deep structure we do not yet grasp. Imagine if censorship failed, if we looked into the heart of a singularity. The sight would not be a picture, but a breakdown of reality itself. Our equations would give infinite answers. Predictions would dissolve into contradictions, and the concept of physics as a universal language might collapse with it. Even now, naked singularities are not entirely banished. Some alternative theories of gravity predict their appearance. The mathematics of modified relativity sometimes produces them without horizons. In string theory and loop quantum gravity, strange geometries can allow horizons to dissolve, and the speculation remains alive. What if singularities are not always hidden? So black holes may represent the compromise. Singularities exist, but horizons hide them, preserving the order of physics. The veil of the horizon ensures that observers outside never see equations fail. In this way, the universe protects itself from chaos, and the mystery is whether this is a law of nature or a coincidence of geometry. When Penrose introduced cosmic censorship, it was only a conjecture, no proof, no guarantee. Decades of study have not confirmed it universally, but still, astrophysical evidence leans toward its truth. All observed singularities remain cloaked, and the question lingers. Does nature always draw the curtain before its stage collapses? Every new observation tests censorship indirectly, by probing spins, by measuring gravitational waves, by watching horizons. The ripples from mergers might reveal cracks, subtle deviations hinting at naked interiors. Some scientists search for echoes in the aftermath of mergers, signals bouncing off surfaces that should not exist. And the silence of such echoes supports horizons, though the evidence is not yet final. Perhaps the greatest irony is that censorship protects us from answers we desperately want. The singularity is where the secrets of quantum gravity lie. The laws of relativity and quantum mechanics both break there, but horizons deny us access. If information about singularities is hidden, we may never see the details directly, and the search for a theory of everything may remain confined to the surface, not the core. Still, physicists are imaginative. They propose thought experiments, simulations, mathematical explorations. The goal is to peer past the veil without breaking its rules. Through holography, perhaps horizons themselves contain the data of singularities, and the hope is that by reading the horizon, we glimpse what lies beyond without censorship ever failing. So horizons are paradoxical. They hide chaos, but they may also hold its solution. The surface of a black hole could be more than a boundary. It may be a canvas of quantum information. In that picture, censorship does not deny us truth, but reframes it. And the future of physics may depend on learning to read horizons, not to cross them. Every discussion of boundaries leads back to philosophy. What does it mean for nature to hide itself? The idea that horizons are necessary implies intention, as though the universe has rules to protect its own story. If true, then order is not accidental, but enforced by geometry. And the implication is that reality itself values consistency above transparency. Every time we study black holes, we see echoes of the universe itself, beginnings and endings wrapped in the same paradox. The Big Bang was itself a kind of singularity, a moment where density and temperature reached infinity, where laws of physics ceased to apply. In a sense, the birth of the cosmos mirrors the death throes of stars and galaxies, and the truth may be that to understand the universe, we must first understand black holes. When we look backward in time, the universe contracts in our equations, galaxies rushing closer, density increasing without end. The extrapolation leads us to a singularity, a boundary of our models. At that point, space-time itself may emerge from quantum origins, and black holes mirror this beginning, singularities hidden in darkness yet born of collapse. Perhaps the greatest link is that both horizons and the Big Bang hide their cause. Beyond them lies physics we do not yet possess. The cosmic microwave background is the horizon of the early universe, light released when the cosmos became transparent. Like a black hole horizon, it blocks our sight of what came before. And the parallel suggests that the universe itself may be a black hole turned inside out. Some cosmologists propose that our universe began from the interior of another black hole, that the Big Bang was the bounce of matter in a larger cosmos. In this view, every black hole births a new universe inside its singularity. Our own existence would then be one child in an endless family tree of universes. And the concept is staggering. Black holes not only end worlds, but seed new ones. So, the study of black holes is also the study of cosmogenesis, the emergence of universes from collapse. The idea remains speculative, but it fits with our ignorance of what singularities truly are. If space and time can begin, they can also recycle, reappear, be reborn from collapse. And the possibility links the death of stars to the birth of cosmos. Even dark matter and dark energy may be tied to black holes, those invisible substances that dominate the universe. Dark matter bends light and anchors galaxies, yet it does not shine. Primordial black holes formed in the first second could account for some or all of this unseen mass. And the search for them is one of cosmology's greatest quests. Dark energy, which accelerates the expansion of the universe, may also find explanation near horizons. The vacuum energy of quantum fields could interact with horizons in ways we barely grasp. Some physicists speculate that the universe's acceleration is connected to horizon entropy, the statistical weight of information stored in space-time. And the link between expansion and horizons may be deeper than coincidence. When we measure black hole entropy, it is proportional to horizon area, not volume, a clue that the universe itself is holographic. The cosmological horizon of our universe also carries entropy, suggesting similar laws. So perhaps the same rules that govern black holes also govern the cosmos at large. And the boundary of the observable universe is itself a kind of horizon. Every observer in the universe has their own horizon, defined by the finite speed of light and the age of the cosmos. The edge of what we can see is not an absolute edge, but a limit of observation. Black holes teach us that horizons are relative, not absolute. They depend on the observer, and the lesson is that the universe itself has a horizon shaped by perspective. Imagine standing on a distant planet, billions of light years from Earth. Your horizon would contain a different slice of the cosmos. The truth of the universe is not one picture, but many overlapping horizons. In this way, cosmology mirrors relativity, perspective defines reality, and the paradox of horizons becomes the structure of the cosmos itself. Even the end of the universe is reflected in black holes, for they may dominate its final chapters. In a cold future, stars will die, Galaxies will fade, and only black holes will remain. Over trillions of years, they will evaporate through Hawking radiation, and the universe will grow dark and quiet, filled with fading whispers of horizons. So, black holes are both the earliest and the last actors, born in the first seconds, dying in the last. The cycle of the cosmos is written in their existence. If primordial black holes seeded galaxies, then they shaped everything we see, and their evaporation will shape what is left when the stars are gone. Perhaps the ultimate fate of the cosmos is heat death. Black holes evaporating, radiation spreading, entropy maximizing. The end would be silence, no structure, no stars, only thin energy. But some propose other endings: big crunches, big bounces, new births from collapse. And the possibility remains that black holes hold the key to which scenario unfolds. Every attempt to describe cosmic destiny touches black holes because they are entropy itself made manifest. The entropy of a single supermassive black hole exceeds that of all surrounding stars combined. If entropy drives the arrow of time, then black holes are its engines. And the future may be dictated by their slow evaporation. When a black hole evaporates, its final moments may be spectacular, releasing all its mass in a burst of radiation. The last stage could shine brighter than a galaxy for a fraction of a second. Primordial holes, tiny ones, may have already died this way, leaving flashes in the cosmos. And the hunt for such signals continues, though evidence is elusive. Even without confirmation, the connection between horizons and entropy is secure. They are thermodynamic objects, not just geometric. The laws of black hole thermodynamics mirror the laws of heat and energy. Their temperature is low, their entropy enormous, their behavior statistical. And the insight is that space-time itself may be emergent from microscopic degrees of freedom. So, the study of black holes becomes the study of the universe itself, from its birth to its death. The boundaries they create reflect cosmic horizons. The singularities mirror the Big Bang. If time has an origin, it looks like a horizon. If it has an end, it looks like evaporation. And the story of the cosmos cannot be told without the story of black holes. Every part of cosmology is colored by their presence. Galaxy formation, structure growth, expansion, entropy. The threads of black holes are woven through the entire fabric of the universe. They are not accidents, not footnotes, but essential elements of creation. And the lesson is that in studying them, we are studying ourselves. Every black hole stretches our sense of dimension, bending the stage on which matter and light move, reshaping what direction even means. The geometry of space-time curves around its mass. Radial lines that once pointed outward now spiral inward without escape. Near the horizon, distances warp, angles twist, paths collapse. And the truth is that black holes reveal the fragile assumptions behind our idea of dimensions. Perhaps the most alluring possibility is the wormhole, a tunnel linking distant regions of space and time. The mathematics of Einstein's equations permits such solutions called Einstein-Rosen bridges. In principle, the interior of a black hole could connect to another place, and the dream is that horizons are not ends, but gateways. So far, no natural wormhole has been found, and the equations suggest they collapse too quickly to use. The stability of wormholes demands exotic matter, negative energy densities that may not exist. Still, theory keeps the door open, hinting that perhaps quantum effects hold them open. And the question lingers: are wormholes fantasy or a hidden feature of black hole geometry? Even without wormholes, holography forces us to rethink dimensions. suggesting that depth itself may be emergent. The principle says all the information inside a volume can be described on its surface. Applied to black holes, this means horizons carry every detail of what falls in. And the lesson is that 3 dimensions of reality may arise from 2. Imagine a book whose entire story is encoded on its cover, the depth and illusion from surface data. The holographic principle suggests the universe itself may work this way. Black holes then become laboratories of holography, showing how dimensions emerge from information. And the implication is profound, that space itself is not fundamental, but derivative. When physicists study string theory, extra dimensions appear naturally, small, curled-up directions beyond our senses. The idea is that particles are vibrations of tiny strings, whose modes require more than 3 dimensions. In these theories, black holes probe those hidden spaces, stretching strings to their limits. And the behavior of horizons might reveal clues to those unseen dimensions. Every time strings are pushed to black hole densities, strange effects appear: entropy, holography, fuzzball states. The consistency across these approaches suggests a deeper unity. Perhaps black holes are keys to linking gravity with quantum theory, and the doorway to that unity may be hidden dimensions. Even loop quantum gravity, which avoids strings, predicts discreteness, space-time woven into tiny quanta at the Planck scale. In this view, singularities dissolve, replaced by bounces or finite cores. Black holes then become bridges to new regions, not infinities, and the structure of dimensions is granular, not smooth. Perhaps horizons are only the outer skin of deeper dimensional shifts, folds where space and time trade roles. Inside the horizon, moving inward becomes as inevitable as moving forward in time. The swap of dimension shows how fragile our categories are, and the singularity is not just a point, but a breakdown of dimensional meaning. Every extension of relativity into extra dimensions raises possibilities, black holes stretched into black strings, black brains. The mathematics of higher dimensions permits objects stranger than our 3-dimensional imaginations allow. Some solutions describe black holes that leak into extra-dimensional space. And the prospect is that experiments might one day reveal evidence for such hidden structures. When particle accelerators were first built, some speculated they could produce microscopic black holes, gateways to extra dimensions. The fear was unfounded, but the math suggested the possibility. No evidence was found, but the search sharpened our understanding of high-energy physics. And the question remains: do black holes hint at worlds beyond our visible 3? Imagine falling into a black hole where dimensions unravel, where length becomes time, where depth becomes information. The experience would be incomprehensible to human intuition. We live in 3 dimensions of space and 1 of time, but horizons may weave more. And the mystery is whether our universe is only a projection of a higher reality. Even cosmology may hold holographic clues, the entropy of the universe tied to its horizon area. The similarity to black holes suggests a shared rule, that cosmic depth is surface data. If true, then the expansion of the universe is an unfolding hologram, and the origin of time may lie in the same laws that govern horizons. So, black holes link us to ideas of emergent space-time, geometry born from information, depth born from surfaces. The shift is radical, replacing substance with data as the foundation. If matter and energy are outcomes of information, then horizons become the true stage, and the future of physics may see reality itself as computation. Every proposed theory of quantum gravity is tested first against black holes, for no other object probes dimension so harshly. The entropy, the radiation, the holographic data, all must be explained. If a theory fails here, it cannot describe the universe, and the benchmark of black holes remains the hardest test. When we listen to gravitational waves, we may hear dimensional whispers, deviations from relativity hinting at new physics. The templates used to match signals already test extra-dimensional models. So far, Einstein still reigns, but future precision may reveal cracks. And the hope is that black holes will betray the hidden scaffolding of reality. Perhaps wormholes are real, stabilized by quantum effects, but too small to traverse. The mathematics suggests quantum foam may connect regions at the tiniest scales. In this vision, space-time is riddled with tunnels, though invisible to us. And the idea that black holes are large-scale wormholes remains tantalizing. Even if wormholes exist, causality itself may resist their use. Paradoxes multiplying with time travel. The universe may close such paths, preventing loops that violate consistency. If so, wormholes could exist but never permit changing the past. And the censorship extends not only to singularities but to time itself. Every paradox we have faced in black hole physics has pointed not to failure but to opportunity. Cracks in old theories where new light enters. The battle between relativity and quantum mechanics seemed irreconcilable, but black holes now guide us toward a synthesis. At their horizons, we see geometry and quantum information meeting, two languages describing one truth, and the patterns emerging are clearer than before. Hints of a deeper framework. When Hawking radiation was first proposed, it seemed to doom information. Particles escaping without memory, horizons evaporating into silence. But decades of thought reframed the problem as one of encoding, not destruction. The idea that horizons hold information has grown stronger, supported by holography and entropy, and the shift is profound. Black holes no longer erase, they store. So the holographic principle becomes more than a clever metaphor, it becomes a working rule of nature. The horizon encodes the information of everything that falls within, scrambling it but never destroying it. In this sense, the horizon is a library, though its script is in a language we do not yet read, and the confidence grows that no data is lost, only transformed. Even. The paradox of firewalls begins to soften under this view. The violent blaze may not exist if horizons are information-rich surfaces. The smoothness promised by relativity can coexist with quantum encoding. If true, then an infalling traveler feels nothing at the horizon, while the outside sees information stored there, and the contradiction is resolved by realizing both pictures are valid at once. Perhaps this is the essence of complementarity, the notion that no single observer sees the full story. The outside sees frozen images on the horizon, information smeared across its surface. The inside sees smooth passage, a journey unhindered by fire or walls. And the reconciliation is that both perspectives are true, though mutually exclusive. Every step forward in physics has demanded such dual views, light as both particle and wave, matter as both solid and field. The lesson of black holes may be similar, horizons as both surfaces and gateways. They are boundaries and records, traps and teachers, prisons and libraries. And the future of physics lies in uniting these contradictions into one framework. When we calculate black hole entropy, the numbers line up with holography perfectly. Area, not volume as the measure. The match is not coincidence, but signal. Entropy scales with the horizon surface, encoding information like pixels on a screen. And the implication is clear. Space-time itself is emergent from information. Even time may arise this way, not fundamental, but statistical, born of correlations. The arrow of time would then follow entropy, written in the bookkeeping of horizons. If true, black holes reveal why time flows forward, why past and future are not symmetric. And the answer to one of philosophy's oldest questions emerges from physics of horizons. Perhaps gravity itself is emergent too, not a force, but a side effect of information dynamics. The idea of entropic gravity suggests that space-time curvature arises from thermodynamic principles. In this view, horizons are not just geometric, they are statistical boundaries, and the law of gravity may be the law of entropy written large. So, black holes take us from paradox to principle, from confusion to clarity. They teach that singularities may be unreachable, but horizons already reveal the truth. If information survives, then relativity and quantum mechanics can coexist after all, and the tension between them begins to dissolve, replaced by synthesis. Every detection of gravitational waves sharpens this vision. Signals match relativity, yet leave room for quantum imprints. The precision of measurements grows with each year. Someday, soon, subtle deviations may reveal the fingerprints of new physics, and the prospect is that black holes will deliver the long-sought theory of everything. When we imagine the end of black holes, evaporating into radiation, clarity deepens. The information must emerge, encoded in the outgoing light. The challenge is in decoding, not in survival. Quantum mechanics demands that the puzzle be solvable in principle, and the confidence of physicists grows that Hawking radiation hides answers in its subtle correlations. Even if we cannot yet measure such faint emissions, we can model them, mathematics tracing entanglement and scrambling. The page curve predicts how information flows out of evaporating horizons. It shows that entropy first rises, then falls, preserving data overall, and the curve offers the clearest sign yet that information is not lost. Perhaps the singularity itself is not the puzzle to solve, but the horizon, the surface where relativity and quantum mechanics meet. The focus of physics is shifting outward, away from unreachable cores. In holography, the surface is everything, the interior an emergent illusion, and the shift brings clarity. The paradox is solved not at the center, but at the edge. Every new theory of black holes converges here: holography, complementarity, entanglement, emergent spacetime. The threads weave into one tapestry, not yet complete, but coherent. Relativity gives the geometry, quantum mechanics gives the information, and the union of the two appears at horizons where their rules overlap. When we see this clearly, black holes stop being destroyers and become teachers, laboratories of ultimate physics. The horizon is no longer a one-way wall, but a record keeper. Its surface is the meeting place of all fundamental laws, and the path forward is illuminated even if the final steps remain unknown. Even philosophy bends toward this clarity. Questions of determinism, reality, and knowledge reframed by physics. The paradox of knowledge itself is reflected in horizons. No single observer can see the whole truth. But together, perspectives make a consistent story, one outside, one inside. And the truth is that reality itself may be perspectival, yet complete. Perhaps the fog was necessary all along. Paradox as the crucible where clarity is born. The frustration of contradictions forced deeper thought, sharper theory, bolder ideas. Without Hawking's paradox, we might never have considered holography. And the gift of black holes is not only mystery, but direction. The closer we come to the end of this exploration, the more we feel that black holes are not anomalies, but windows into the deep laws of nature. Every paradox, every contradiction, every strange prediction they force upon us seems less like a failure of science and more like an invitation. The invitation is to imagine reality not as a fixed, rigid stage, but as a fabric still being woven, a structure whose threads are information, geometry, and time. And in studying black holes, we are not only asking about distant monsters in the sky, but about the very rules that allow reality to exist at all. Even now, as we grasp at holography, as we wrestle with entanglement, as we debate complementarity, the fog begins to thin. The truth emerging is not one of destruction, but of preservation. For all our fears that black holes erase what enters them, the growing weight of theory insists otherwise. And the clarity is this: nothing fundamental is lost, not even when swallowed by horizons. Perhaps this is the deepest lesson of all. That the universe is conservative at heart, that its ledger always balances. The laws of physics may seem brutal, may hide truths behind barriers, may scramble detail beyond recognition, but still, they preserve the record, like a library burning in slow motion, yet never destroying its pages. And the idea that horizons are cosmic bookshelves, not graves, reshapes how we view everything. When we consider black holes as libraries, their entropy takes on deeper meaning. The Bekenstein-Hawking formula, linking entropy to surface area, is no longer just mathematics. It reveals that the number of possible microstates grows with area, not with volume. And the lesson is clear. The universe keeps its memory in surfaces, not depths. Every horizon is then a page, written not in ink, but in correlations of quantum fields. The letters are entanglements, connections between particles inside and out. Though we cannot read the script, it encodes everything that has ever crossed. And the meaning of entropy is no longer disorder, but compressed order waiting for the right key. Even space-time itself may be emergent from this book of correlations. The idea of entanglement as the fabric of geometry has gained strength in recent years. In this vision, space is not the background stage, but the web of relationships between quantum bits. And the gravity that curves space-time is simply the flow of information reshaping itself. Perhaps, then, black holes are the purest form of this principle. Condensed knots of entanglement, horizons of information density. The singularity is not the story, for it is hidden, unreachable, irrelevant to the data encoded at the edge. What matters is the surface, the horizon where geometry and information unite, and the shift in focus moves physics away from despair and toward comprehension. Every paradox that once seemed insoluble dissolves under this new framing. The firewall becomes unnecessary, for smooth horizons can coexist with information storage. The loss paradox weakens, for radiation can be entangled with interior states in subtle ways, and the apparent contradictions become perspectives on the same deeper unity. When we step back, the picture grows almost poetic. The universe guards its secrets not by erasing them, but by scattering them so finely that only the whole system holds the truth. No observer sees everything, the traveler falling in, the astronomer watching from afar. Each carries part of the story. And the lesson is humility. that reality is bigger than any single perspective. So, this clarity brings us closer to a unification of physics, not by eliminating paradox, but by reframing it. The language of information becomes the bridge, capable of speaking to both relativity and quantum mechanics. Space-time geometry listens to entropy, while quantum fields obey conservation of data. Every detection we make, every gravitational wave, every shadow image tightens this picture. The Event Horizon Telescope gave us a ring of light, the silhouette of M87, the first direct glimpse of a horizon's edge. In those photons bent by gravity, we saw geometry revealed, and the confirmation was breathtaking. Black holes exist as we predicted, yet invite questions we never foresaw. Even gravitational waves tell this story of clarity. The chirps of colliding horizons match relativity to exquisite precision, yet leave space for quantum whispers. Each merger we record is another chapter, another chance to test the edge of theory, and the anticipation grows. One day, tiny deviations may betray the fingerprints of deeper laws. Perhaps that day will come when detectors grow more sensitive, when we build instruments in space. The Laser Interferometer Space Antenna, LISA, will listen to slow, deep waves from giant black holes merging. Its ears will catch signals that last months, carrying details we have never seen. And the analysis of those waves may confirm or challenge holography itself. So, the horizon becomes the stage where future physics will be tested. The quantum imprints in Hawking radiation, the entanglement patterns in wave echoes, the entropy of cosmic horizons. All roads converge here, at the surfaces where information is written. And the truth is that black holes are not accidents, but central laboratories of the universe. Even philosophy cannot escape the clarity emerging here. The questions of determinism, of fate, of free will, take new meaning under the rule of horizons. If information is always preserved, then the past cannot be erased, even by collapse. And the future may not be freedom, but the unfolding of data already stored. Every human has wondered about immortality, about whether traces of us survive. The physics of black holes suggests that in some profound sense, nothing is ever lost. We fade from sight, our details scrambled, our signals weakened, but the record remains. And the comfort is that the cosmos itself is the ultimate archivist. When we think of death in stars, in galaxies, in people, black holes remind us that endings are never absolute. The horizon does not erase, it transforms. Information continues in new forms, inaccessible perhaps, but not gone. And the analogy may comfort us. Loss is transformation, not annihilation. Even the end of the universe itself may be framed this way. The heat, death, the evaporation of black holes, the fading of galaxies, all still preserve the ledger. Nothing vanishes entirely. It is only redistributed, encoded, hidden. And the destiny of everything is not oblivion, but dispersal. Perhaps this is why studying black holes feels so profound to us. It resonates not only with physics, but with meaning. The questions they raise are not only about equations, but about survival, permanence, identity. We ask whether the cosmos forgets, and black holes whisper no, it does not. And the answer is that memory is written into the very structure of space-time. Every journey to understand black holes is also a journey to understand ourselves. The atoms in our bodies were born in stars, their fates tied to collapse and horizons. In studying black holes, we are studying our own origins, our own destiny. And the realization is humbling. We are not separate from the cosmos, but written into it. So, as clarity emerges, we see black holes not as monsters, but as mirrors. The mirror shows us the fragility of our theories, the incompleteness of our understanding. But it also shows us resilience, that physics adapts, that contradictions breed progress, and the reflection is inspiring. We are capable of chasing answers even at the edge of reality. When we reach this point, the paradoxes feel less frightening, more like guides. The firewalls, the fuzzballs, the holograms are all attempts at the same truth. Each framework is a language describing the same horizon in different dialects. And the convergence is that information is eternal, geometry is emergent, and horizons are where the two meet. Even the singularity, once the ultimate terror, now seems less important. The horizon has stolen the spotlight, for it is accessible, measurable, meaningful. The singularity may remain hidden forever, its details irrelevant, and the focus shifts outward to the place where physics can still be read. Every thought experiment leads us back here. The astronaut falling in, the observer watching outside, the entangled pairs at the edge. They all converge on the same message. Horizons store, they do not erase. And the unity of these perspectives confirms the clarity. Perhaps this is where our story must pause, not because answers are finished, but because clarity has begun. The cosmos has given us riddles, but it has also given us tools. We listen with gravitational waves, we see with telescopes, we calculate with quantum theory. And the progress is undeniable. We stand closer than ever to understanding. Even if final answers remain out of reach, the path is lit. The horizons of black holes are no longer only symbols of ignorance, but beacons of knowledge. They mark the place where contradictions sharpen into synthesis, and the vision of a unified physics shines faintly, like starlight just above the horizon. Every end we have described is also a beginning. Collapse into creation, evaporation into radiation, paradox into clarity. The lesson of black holes is that nothing ends absolutely. So, perhaps, the story of physics itself is endless, each conclusion feeding the next chapter. And the comfort is that the cosmos is not silent. It is always whispering if we know how to listen. The closer we come to horizons, the more they resemble us, fragile, paradoxical, yet enduring. In the darkness of black holes, we find not only the death of stars, but the persistence of truth. And the clarity that emerges is not only scientific, but human. It tells us that though we fade, though we collapse, though we scatter, our traces endure. Every question black holes force upon us reflects a deeper hunger, to know whether the universe itself makes sense. The answer, faint but growing, is yes. Though chaos and paradox surround us, order is hidden within. And the story ends not with despair, but with light that refuses to be lost.